Hello, everyone. Earlier today in my Physics 241 class, which is calculus-based physics or physics for scientists and engineers, the first semester one, I was actually solving a problem regarding uh, two cars passing each other on the highway going in opposite directions. One was a police car, and the other one was a speeder. And the speeder at the time was going 80 miles per hour, and the police car was going 60. It took about a second for the police car to register. So the police car passed the speeder by about a second, then began to slow down at 4 meters per second. Came to a stop. Took about 3 seconds to turn around after coming to a stop where they moved appreciably no appreciable distance, and then accelerated up to 100 miles per hour at 5 meters per second every second, and then continued at that speed, 100 miles per hour, until they caught up. And the question was, how long did the speeder drive after they were side by side, obviously facing opposite directions, and how far did they travel? So I didn't like the way it worked out. It was a long, kind of convoluted problem. The video didn't go so well. So I decided to go ahead and make another one. I typed up the actual problem, and then I worked out the solution. So let's begin with that. I'm going to start off sharing my screen so you can see the actual problem. So this is a police car traveling west at 60 miles per hour passes a speeder doing 80 miles per hour toward the east. It takes the officer about 1 second to begin slowing down. Notice I've fixed all the sig figs. Everything's like 3 sig figs or more. The officer can decelerate safely at about 4 meters per second every second, and then once she comes to a stop, she loses another 3 seconds turning around. She then accelerates at 5 meters per second every second until she reaches 100 miles per hour. At that time, she continues at 100 miles per hour until she catches up to the speeder. How long will the speeder travel at 80.00 miles per hour beyond where the officer spots him, which was at 1 second before she started to slow down? And B, how far will the speeder have traveled? So we're going to solve that problem. As always, you can actually download the actual documents I write up as well as the typed problems I write up. You can download those uh, from my Google Docs. All you have to do is email me, and my email is Billy, Billy, at physics, PHYSICS solutions, SOLUTIONS.com. So I hope you enjoyed the solution. Let's get started. I'm going to stop sharing my screen now, and I'm going to switch to my document cam. And the big thing with this problem is you really need to sort of keep track of all the stuff that's going on. And of course, we first need to convert all those miles per hour to actually meters per second so that our equations work with more reasonable units of time. You could use miles per hour with all the equations we use. However, the problem is you'd have to use time in units of hours. So I'm going to start off with just a conversion that I already did. You all should be able to verify this. First off, 60 miles per hour, which is written mph, is the equivalent of 26.82 meters per second. And then 80 miles per hour. 80 miles per hour is equivalent of 35 point, let me double check my math, 35.67, if I remember correctly, meters per second. 35.76, excuse me, 35.76 meters per second. And then finally 100 miles per hour. Notice these are all in different directions. I'm going to make use of something called displacement a little later, where I'm talking about sort of vector quantities. So the car was originally going west, the police officer's car, so that one would be in a negative direction because I'm going to call east the positive direction. The speeder was going 80 miles per hour in the positive direction because that's east. And then, of course, the police officer will go 100 miles per hour in the positive direction as well. And that 100 miles per hour is 44.70 meters per second. Obviously, it'd be a lot easier if I'd given you the numbers in kph, but I wanted to keep it a little more real for what everyday Americans taking my class are more used to. Not that they shouldn't be more used to dealing with the MKS system. So first off, I want to consider what's going on here because I need to keep track of everything that transpires. So first off, The speeder gets an extra 1 second of travel, 1.00 second of travel for just the police officer's reaction time. So one is 1.00 seconds to react. And by to react, I mean the police officer is going to react take 1.00 seconds to react. And that during that time, the police officer who's going 60 miles per hour is going 26.82 meters per second times 1.00 seconds, which gives us 26.82 meters. And this is in the west direction. So I'll just put a W by it so we'll remember later to actually use a negative direction. Now, what equation I actually use there is actually the definition of average velocity. Average velocity is equal to x minus x0 over t minus t0, but we almost always assume t0 is 0. In this case, I also assumed x0 was 0. And then since it was a constant speed while the police officer was reacting, then V average is actually a correct formula. The V average is the velocity. So we end up getting x is equal to just V times t, and that's V and that's t. Now the speeder, he's going to be going at 35.76 meters per second. There I go again, writing it backwards, 76 meters per second. And he's going to do that for 1.00 seconds. So that's going to give them an extra, of course, 35.76 meters. And that is, again, east. So I'll remember that's traveling to the east and therefore in the positive direction. So that's a little bit of the advantage that they've got. I'm probably not going to make use of this because the way I'm going to solve it is I'm going to just take the speeder from the instant they're next to each other, multiply 35.76 times the total number of seconds traveled, and that'll give me the actual displacement of the speeder. However, with the police officer, I have to do a little bit more. I have to see that it's going to go this way for a little bit, this way for a little bit more, then it's going to sit still for 3 seconds, then it's going to speed up this way for a certain distance and a certain time, and then it's going to go at a constant speed for the rest of it. So I've got to deal with that. So our first part was they were side by side, and then the popo traveled another 1 second at 26.82. So it went negative 26.82 meters. In other words, 26.82 meters to the west. The second interval that we're talking about, the second interval is that it's going to take basically the officer will travel farther west while accelerating. In fact, it's actually decelerating, but we just use the word accelerate in physics. And the acceleration is going to be a rate of 4 meters per second every second. So what I'd like to do is find out how far the police officer is going to go in that amount of time. And I don't really know the time. So, and I don't necessarily need the time right now, but let's first look for an equation that has the final velocity, which we assume will be 0, has the initial velocity, which is 26.82 meters per second, has the acceleration, which is going to be 4 meters per second every second in magnitude. We'll address the sign issue in a second. And it gives us the x. In other words, it gives us the displacement. Well, the equation we're thinking of is one that a lot of physics instructors don't allow their students to use, and that's v squared is equal to v0 squared plus 2a times x minus x0. Again, I'm going to treat the x0 as if it's 0, and that's going to give me that x is equal to v squared, the final velocity squared, minus the initial velocity squared, over 2 times the acceleration. Okay. Now, in this case, the vehicle is going to the left initially very fast. So I have a large negative velocity of 26.82. That's going to be in here. But when you, of course, square that, that's just going to become positive, and then the final velocity is going to be negative. But in slowing down a vehicle going to the left, you're actually accelerating in the positive direction. For instance, you could say negative, you could say your final velocity is 0, and then 0 minus the initial velocity, which was, say, negative 100, would give you negative of negative 100, and then you divide that by the time, and you end up getting a positive. So that's what's going on here. So I'm going to say the final velocity is in fact 0 squared minus, in this case, I'm going to have 26.82 meters per second. And that's going to be squared divided by 2 times the acceleration, which in this case, the acceleration is going to be 4 meters per second every second. So we're going to actually work that out, 4.00 meters per second every second. And I teach my students to use that unit instead of the meters per second squared. When I actually do that division, you can tell that's actually going to come out to be a negative distance, and that negative distance is just indicative of it going to the west. So it's going to be a negative 89.914 meters. Now, I had 4 sig figs, subtracted, didn't really change the sig figs, divided by 3 sig figs. So in principle, I should just have 3 sig figs, which means the 1 and the 4 should not be significant. So I'll underline those. I'll keep them, but I'm going to underline them. Now that gives me how much additional distance the police officer went to the west, in addition to the negative 26.82 that the police officer did. Let's do the police officer. We'll underline them with orange. So this is a police officer distance. And this also is a police officer distance. And we'll underline the speeder with green just to keep them separate. So there's a speeder's distance. Now, we also want to know how long the police officer traveled, and you'll see why later, but I want to figure out the time. So I would like to find out, given the final velocity, which we know is going to be 0, the initial velocity, which we know is negative 26.82, and maybe the acceleration, I'd like to know how long it takes. Well, that tells me I can use the average acceleration equation, which is A average is equal to V minus V0 over, again, T minus T0, but we're just going to call it T. In this case, the acceleration is a constant, so that A average is actually just plain A, and it's right. So I'm going to say T is equal to V minus V0 over A. Again, the A is a positive acceleration because it's slowing down in the negative direction. So the final velocity will be 0 minus the initial velocity, which is negative 26.82 meters per second. And now you see a minus and a minus. And in fact, that's divided by 4.00 meters per second, which is a positive. So this is a positive divided by a positive, which gives us a positive amount of time. That amount of time should be 6.705 seconds. Now I used a 4 sig fig divided by 3 sig figs. The subtraction really didn't mean anything because 0 could be infinite number of decimal places. So I really shouldn't carry any more than 3 sig figs, which means I'm going to underline the 5 to keep track of that being the time that the police officer continued to travel to the left. But this also happens to be the time that the speeder got to continue traveling to the right. So I'll underline it with both colors for that matter. So that's part. Now, the third part of the motion is when, in fact, the police officer has to waste 3 seconds now that they've come to a complete stop just to turn the vehicle around. And we're going to assume that it basically covers almost no distance at that time. And that's probably fairly realistic. So when we do that, we're going to say the police officer turns around. T is equal to 3.00 seconds. And X is just equal to 0. So in this case, again, this is a police officer and, well, the orange is the police officer, and it's a speeder thing. So I'm going to underline it with both colors. But the X equals 0, that's just a police officer thing. So that's the other interval, and this is turning around. So I'm just going to write up there, turning around. And I'll put it in a different color just so we can easily see what that part of the motion was for. This part was slowing down. And this part was reacting. Okay, so we've got our motions. We know what's going on in each of the parts. Maybe the green's not the prettiest color for me to be using with you guys, so I'll probably use that sparingly from here on out. Part 4, now the vehicle's turned completely around, and it's going to accelerate at 5 meters per second every second. In doing so, it's going to keep on doing it until it reaches 100 miles per hour, which we've already converted to meters per second, and we know it's 44.70 meters per second. So first off, I'm going to figure out how far the police car is going to go while speeding up. Again, this may or may not be relevant, but I'm just sort of working it all out so I can then piece it together and figure out how to solve the problem. So if I want to know how far it went, and I want to use the initial velocity being 0, the final velocity being 100 miles per hour or 44.70, and I know its acceleration, then I'm again thinking of using that equation that a lot of physics instructors don't like to use because it's not a vector equation. So I'm going to use that. V squared is equal to V0 squared plus 2A. Again, I'm going to assume X0 is 0. And with that in mind, I'm going to find that X is actually equal to V squared minus V0 squared over 2 times A. Now we're actually speeding up in the positive direction. So the final velocity is going to be bigger than the initial. That's going to make everything positive. It's going in the positive direction, so that's going to be positive as well. And then it's going to be divided by a positive acceleration. So everything's going to come out positive here, which is what we mean for the east direction. So I'm going to say 44.70 meters per second quantity squared minus 0 squared over 2 times 5.00 meters per second every second. When I do that math, I can compute it, and it turns out to be a positive 199.809, 199.809 meters. Okay, now I use 4 sig figs and 3 sig figs, and really nothing happened with subtraction in there, and that's what you got to watch out for on sig figs. So I really should only be using 4 sig figs, which means the 0 and the 9 are bad. Let me use black, since I've been using black to mark the unreliable digits. In other words, I'm supposed to be rounding it to the place that's not underlined. So this is the speeding up process. So let me, again, I said I wasn't going to use the green so much. I'm going to say speeding up. Now I also want to see how much time has gone by, again, because all this time added up is going to be how long the speeder is speeding up. So if I multiply the speeder's speed by, which is 35.76 times the total amount of time, then I'll get the total distance the speeder travels. So if I want to know how much time this took, I can use either make use of the x being that I know the x now, in which case I would use x equals 1/2 a t squared plus v0t plus x0, again, treating x0 as 0. And in this case, since it started from rest, the v0 is 0. So that's not a bad way. There is a reason not to use this figure because I just calculated it. And if I had made a mistake there, then if I use that number, I'm going to get yet another mistake. I'm going to do it just because it's not always true that you can avoid that. So I'm going to go ahead and do it here. And I'll show you that it gives you the same answer the other way as well. So this is going to give me that x is equal to 1/2. The acceleration is 5.00 meters per second every second times the time. And with this case, we actually do not know the time. In fact, that's what we were trying to solve for. So we'll just put a t here. But now that we know the x, we can plug that in. So actually, I was mistaking. I'm actually going to use the x. I'm going to put this x in here and then solve for t and the t squared equation. I'll show you another way where we can do it without using that x. At least I think I can. Yeah, I can. Okay. So I want to say t is going to be equal to 2 times x over a to the square root. Okay. So that becomes the square root of 2 times x, which was 199.809 meters, divided by a, which is 5.00 meters per second per second. Now, this is a good time for you to actually think of it as meters per second squared, because meters divided by meters per second squared, the meters per second squared turns over, and then the second squared is on top, and the meter is on the bottom. That cancels out that meters, and when you take a square root of second squared, you just get seconds. Doing this math, I get 8.94 seconds. And what I'm doing is I realize this from the distance being 809, this was actually only supposed to have 4 sig figs. This one has 3, so 8.94 is the proper number of sig figs. And if I have a calculator to verify that, let me do that real quick. I'm just want to see how many sig figs I should have brought it out to just to carry an extra to be consistent with what I've been doing. So I'm going to take 2, I'm going to multiply that by 199.809 I'm going to divide that by 5. Take the square root of all that, and I get 8.940. So that's why I rounded it to 940. So that gives me the actual seconds. This is the actual seconds that the police officer has to waste again. In this case, it's not so much wasting because at least he's going the same direction, but it's also another amount of time that the speeder will travel. Now, I did, again, as I said, I ended up using a calculated value. If I would have used, let's say, this equation, well, not that pen. Let's say if I use this equation, A is equal to V minus V0 over T, then I could have just found that T is equal to V minus V0 over A, and that final velocity is 44.70 meters per second minus the initial velocity 0, and divide it by 5.00 meters per second. You see that a meter per second divided by a meter per second ends up giving you just a second, and lo and behold, that gives you 8.940 seconds as well. So that would have worked. I just did all that without you reading it on the camera. So I did it the first way using a value X that I had just calculated. And what I did here is use the definition of average acceleration, but in this case, it's a constant acceleration. So average acceleration and constant acceleration are the same thing. So I can put that line to represent the average, or I can leave it off as I did here. The T is equal to V minus V0 over A. The final velocity is 44.70. The initial velocity was 0. The acceleration is 5.00. When you divide, you get 8.940 seconds. So now I've gotten through the vehicle actually speeding up to 100 meters per second, or excuse me, 100 miles per hour. So that brings us to the point at which the police officer now begins to just travel at a constant 100 mile per hour, or 44.70 meters per second. Yes. So in total, the officer has done quite a bit. Okay. What the officer has done is the officer traveled 26.82 meters from part 1, traveled 26.82 meters in the negative direction, and that was just reaction time. Traveled another 89.914 meters in the opposite direction, again, a negative direction. That was in slowing down. Then wasted 3 seconds. That's going to be important to the actual speeder, not so much to the police officer, because the police officer is not going to really change their distance anywhere there. And then beyond that, the police officer finally turned around and then sped up to 100 miles per hour, which is 44.70 meters per second. In doing so, it went a positive distance of 199.809 meters, and it took 8.940 seconds. So what I'm going to do is I'm going to imagine these as displacements as opposed to just, velocities and speeds and distances traveled. I'm going to treat them like vector quantities, so that the 26.82 went to the left. That's the displacement of 26.82 meters to the left. So that's a negative 26.82, as was the negative 89.914. And then I'm going to add to that the positive 199.809. And when I do that, I'm up to basically the point where the police officer starts to go a constant 44.70 meters per second. And I can just multiply that velocity times the time and add it to it. So if I set the displacements equal, so displacement of the popo equals the displacement of the speeder, then I just got to make sure I take into account all the things that were happening. So here's how I do that. So first off, I'm going to write negative 26.82 meters, and that's for the 1 second reaction time that the police officer took. Then I'm going to write another negative 89.914 meters. That's for the police officer slowing down. Then I'm going to add a 0 distance just to remind us that that's the 3.00 seconds that we wasted in turning around. But notice it wasn't a distance, so I didn't really need to add anything there. But now I've got to add the time required for him speeding up, because we know that that particular time and that distance wasn't enough to catch them up with the actual speeder. So we're just going to say plus, since it's now going to the east instead of the west, plus 199.809 meters. Again, the 0 and 9 are not that are really not X digits that we should be counting, just like the 1 and 4 weren't. And now the last part is the police officer traveling at 44.70 meters per second to the east, hence it's positive, times TC, which I'm going to call TC for T chase. So this is the amount of time he's seriously chasing them at a fixed speed. Well, in the meantime, the speeder, from the instant that they were next to each other, the speeder has been traveling at 35.76 meters per second. And that's the velocity, but the speeder got quite the head start. The speeder got 1.00 seconds for the reaction time. The speeder got 6.705 seconds for slowing down while the police was slowing down. The speeder also got 3 seconds, and that's 3 seconds, even though I barely fit the unit in there. They went an additional 3 seconds while the police officer was actually turning around. And then this police officer took 8.94 seconds to speed up. So there's another 8.94 seconds that the speeder got as a head start. And then the rest of the time was T chase. Okay. So what we have to do is now figure out how long this time was. Okay. So if we combine like terms, then what we'll get is 83.075 meters. Notice I'm adding up all of these. The least precise number only has one sig fig or one decimal place. So these last two are doubtful. You might even, no, it's just those last two. And then I'm going to say plus 44.70 meters per second times T chase is equal to, now if I did all these, I do the 35.76 times 1 plus 35.76 times 6.705 plus 35.76 times 300 plus 35.76 times 8.94. When I do all that, I come up with, in fact, 19.645 seconds. That's the total number of seconds. So 1, 7.605, 10.605, 18.605 plus 0.94. So I'm going to call that, like I said, 19.645 seconds times 35.76 meters per second. And then the rest is going to be plus 35.76 meters per second times TC. Again, TC being the chase. Okay, so I now accounted for all the different times. Notice this other time was just stuff that that the speeder had above what the cop had, because the cop was actually doing all this other stuff, just trying to get up to the same speed. So we do all that, and what I end up getting after taking basically all the regular numbers and pulling over here, this number is going to be quite a bit bigger than 83, so it's going to get negative, and then I'm going to subtract this over here. That's quite a bit bigger than 35, so I'm going to get a negative there. That's okay. That's going to give me a positive amount of time. So I get negative 619.4 meters is equal to negative 8.94 meters per second. That's what you get when you do 35.76 minus 44.70 times TC. And that gives us TC, the chase time, is actually 69.29 seconds. And I used, basically in this scenario, I ended up using 3 sig figs divided by 3 sig figs. So technically I should only be carrying it to 3 sig figs. So that's the time that the speeder was traveling at a constant speed at the same time that the police officer was traveling at a constant speed. Now, from here on out, I got to actually figure out what the question was, which was what's the total distance and the total time that the speeder traveled. So the speeder's distance is so the speeder's total distance should be uh, basically you're going to get for the speeder, you're going to get 35.76 meters per second. And during that time period, or that velocity is going to be maintained the whole time. And the times that are going to go by are 1.00 seconds plus 6.705 seconds plus 3.00 seconds. Again, this is the reaction time. This is the slowdown time. This is the turnaround time. And then this is the acceleration time, 8.94 seconds. And then the total time that they're going at constant speed, which is 69.29 seconds. So all that distance, once I add up all those times, I will get a basically 88.932 seconds. So I get 35.76 meters per second times 88.932 seconds. And that gives me a distance of 3,180.2 meters. And again, I should be rounding it based on the sig figs. I should only be rounding it to, in this case, 2 decimal or 1 decimal or no decimal places. So that's what the speeder went. And from the previous math, we also figured out that the speeder time, the speeder's total time from when they were next to each other was in fact 88.932 seconds. Again, I'm giving you way more digits than are necessary. In fact, this one should have only been the 2 decimal places, but that's the 2 answers. Now, the problem with this is Mr. Younger, me, I made up this problem out of my head. So there's really no way to check whether it's right. I haven't had another physicist work the problem or anything like that. But there are ways where you can still test it. So for instance, when you do something like this, it's good to try to solve it another way. And when you do that, if you get the same answer, the odds are very, very slim that you happen to screw up twice and get exactly the same answer both times. So what I'm going to do is I'm going to try to think about how far did the officer travel total, and then subtract from that the part of the travel that was required for the police officer to get back where the 2 cars were side by side. Of course, the second time the police officer will be going in the right direction. And if I subtract that distance away from the total and I get something close to 3180.2, then I'll know that I did it fairly. I'm pretty confident I did it correctly. So to that end, let me show you a little extra calculation. So how far did the police officer go? So the police officer would have went, first off, he would have went positive 26.8, because I'm counting everything like the odometer we read. Everything's a distance. If you remember Ferris Bueller's Day Off, they put the vehicle in reverse to try to run down the odometer miles. But it turned out that that was not a vector odometer. It just measures distance. So it actually was making the miles even worse. So 26.82 meters for the 1 second that it took them to realize, oh, I gotta catch this person, plus the 89.914 to slow down. Again, I should be using the sig figs rules so that 0.14 goes under there. There's no uncertainty here. Well, actually, you should probably maybe put uncertainty on that digit, because the second was 1.00. So 3 sig figs times 4 should give me 3. Then, of course, he went 0 meters for turning around. So we get to ignore that. And then we went 199.809 meters and speeding up to 100 miles per hour. And then he went 44.70 meters per second times 69.29 seconds. That was the total distance traveled by the police car. If you add up all that, you end up getting 316.543 meters plus 44.70 meters per second times 69.29 seconds. And that gives me 3,413.8 meters. That 8, I shouldn't be calculating. So this is something I can check. So that's the total distance traveled. Now, if I figure out how much of that was wasted, in other words, how much went to the left and then how much went back to the right just to get where the cars were when they initially were next to each other. Now, if I subtract that from this and get about the 3,180 that I got earlier, then I'll be fairly confident that I didn't make any mistakes. So what I'm going to do now is I'm going to say that the police officer, in fact, went west 26.82 meters. So that's a negative, in other words. And the police officer then went 89.914 meters. And that was west as well. That was in slowing down. But then while it was getting back up to that position, the police officer would have had to go east 26.82 meters. And then it would have to go another 89.914 meters. And that would just bring it back to basically where it started to slow down, or actually in that case, where it's actually got beside the car. So if I do the math here, what I will get is this distance plus this distance plus this distance plus this distance. Without the signs, all the signs will be positive. Then I'll end up getting the total distance is 233.468. So let me, just in case somebody gets confused, I don't want you thinking of that as if I'm adding negatives and getting this. I'm just going to write that this is west and this is west and this is east and this is east. Okay. So I'm adding up all that. That gave me 233.468. We already talked about the units. It's probably one decimal place is all we're really supposed to do. So now if I subtract that from the total distance, so if I do 3413.8 meters minus 233.468 meters. Okay. This one's actually a doubtful digit anyways, but when I do that subtraction, lo and behold, I get 3,180.3 meters, but we weren't really supposed to count that anyways. So that's exactly the distance that we got, at least to the proper number of sig figs, 3,180, 3,180. That means we've got a great check that our math worked out properly. So that's a way you can solve a fairly complex vector problem in some sense, because we actually were taking into account the direction. We were going left and right. So that's a way you can actually solve that problem. Just to see the problem again, I'll go ahead and share the screen. Everybody should be able to see exactly what we did here. And as I said, I will be putting these documents on my Google Docs, and you can email me at billy@physicsolutions.com. Here that email address is again, Billy at, and you will see that I don't type it on the YouTube channel because then I'll get a bunch of spam. So it's physics, PHYSICS, solutions.com. So if you email me that and tell me exactly which episodes you want or whatever, I can give you access to the actual documents that I'm writing up, as well as various versions of the problem I worked out, and so on and so forth. So let me finish this up with just letting you look at the problem again. So that was the problem. A police car traveling west at 60 miles per hour passes a speeder doing 80 miles per hour toward the east. It takes the officer 1 second to begin slowing down. The officer can decelerate safely at about 4 meters per second. And then once she comes to a stop, she loses another 3.00 seconds turning around. She then accelerates at 5 meters per second every second until she reaches 100 miles per hour. At that time, she continues at 100 miles per hour until she catches up to the speeder. How long will the speeder travel at 80 miles per hour beyond where the officer spots him, which is when they're right next to each other? And how far will the speeder have traveled after that time? So we've now worked all that out. And I hope that's helpful. Have a good day.